Good morning, everyone. Welcome back. So today, what I'm going to try and do is sort of like to pick up from where we left it yesterday, and I'll try to finish off what I call lecture 2, and then we'll start on lecture 3. So I think I'm about like an hour. I have an hour delay of what I plan to do, but I guess that's like too much material, but that's okay. So just a brief summary of what we were trying to do yesterday. So we decided to compute relative corrections to our Drediani process, assuming the pattern model. So we started by looking at group diagrams, and we argued that there may be ultraviolet divergences that can be absorbed by standard renormalization procedure. And then we noticed that there are infrared divergences as well, and which we regulated the same way as we do for the UV, namely we use dimensional regularization. And in particular, we saw that in visual correction, we have a 1/epsilon square pole and a 1/epsilon pole. And crucially, the visual corrections have the same kinematics of the bore. And so they, if you want, they're multiplied by a delta function that fixes the tau hat, this ratio of the Q squared divided the platonic central mass energy to be equal to. Then we sort of sketched the real correction diagrams, and we saw that crucially now tau hat is not necessarily equal to 1. Okay, because the kinematics now is a 2-to-2 kinematics, and so the central mass energy doesn't have to go necessarily all into forming the plus loaded circles. And so I wrote down the results. Indeed, we do have contributions which are delta functions that are called endpoint contribution, and they actually are multiplied by 1/epsilon poles. And so what we see is that the 1/epsilon square pole and we also have a 1/epsilon pole which have the same coefficient, the delta function times the number, with opposite sign with respect to the visual correction. So when we sum, because we want to be inclusive, the real and the virtual corrections, these poles cancel. However, we also found that there's a 1/epsilon pole which comes with a coefficient which is not a delta function. It's a distribution, but it's a more complicated distribution or function, the tau hat. And then there's a finite part which I call the QQ bar. This coefficient is very famous and is called it's the leading order Altarelli-Parisi splitting function for the splitting of a quark into a quark. So we have to sort of try to understand like what to do with the singularities. I remind you that there's because we use dimensional regularization, there is a scale in our calculation, which I generically indicated as mu, but this will play the role of the scale mu f, this factorization scale that we briefly sketched or discussed yesterday. Now, before telling you what to do with these singularities, in the spirit of being fully inclusive, and that's something that actually already in the first day some of you pointed out, we should ask ourselves, like, we know, like, why are we only considering quarks in the pattern model? So we addressed this issue yesterday. Well, this issue historically, that was what the experimental evidence suggested. If you remember, we had this Callan-Ross relation, which suggested a spin a half particle interacting with the photon. But now, actually, if you go to order alpha S correction, you see that nothing, in principle, forbids you to consider other. We understand the patterns. We should identify them as quarks and gluons, and so you can also pick up a gluon from the proton. So you can also have the possibility that the pattern that takes part that goes into the Hall interaction being a gluon rather. And indeed, this is actually there is experimental evidence for this as well if you go back to deep inelastic. So if you do more precise experiments, you see that this Callan-Ross relation is violated when you go at some level in experimental analysis. And indeed, you can show that this is violated if you go to order alpha S correction. Indeed, there's in deep inelastic scattering, this is the way we parameterize this is by introducing a new structural function, which is called the longitudinal structural function FL, which indeed starts at alpha S. So if you also are happy to include the possibility that one can pick up the gluon in the initial state, then we should also consider this type of Feynman diagrams. That's not fun. Okay, say P1. Let's go K. P2, and this was called Q. Also, disappear. Okay. And you can ask yourself, like, can we pick up a gluon from both? I mean, you see that these when you square them, you get like an order alpha S contribution. So they belong to the class of contributions that we want to include. You can ask yourself, what about picking like a gluon for each of the protons? So you can imagine writing diagrams like that. But you see, in order to couple the gluon to and produce an electroweak boson, then you really have to draw this sort of diagrams. And you see then that you need, if you want to pick up a gluon from each proton, you need two strong couplings, two vertices with some interaction. And so this leads to high order correction in the coupling. Okay, so this will be an order alpha squared contribution. So we neglected this to this order. Now it is true that we have many gluons. The gluon PDFs is enhanced at the LHC. So this contribution, although is one order down in the power expansion, may be important from a numerical report. But if you're strictly speaking with perturbation theory, then you don't have to do this. Now you see, we can do this calculation, and now we notice we can already say a few things like these type of contribution don't have any, like they don't have a corresponding virtual correction order at this order. Okay, these are pure real contribution, and so we don't expect any 1 over epsilon square or 1 over epsilon times the delta function. And indeed, that's what happens. So if you do this calculation, you'll find again. I mean, you can always factorize the Born. That's your choice. 4 alpha S over pi, similar contribution. Scale. So half size. I guess one warning, which I'll probably got wrong here, it's need to be checked. Be careful if you take results from books, so you want to cross-check the calculation you've done with the book. Be careful that out there are two conventional. Some books or some papers, they use d equals 4 minus epsilon. Other, they use 4 minus 2 epsilon. And of course, there's this is a factor of 2 difference, but now I'm wondering that this gamma might be 1 minus epsilon over 2. But okay, so I can check it later. And here, indeed, you don't have any delta function contribution, but you do have an epsilon pole multiplied by a different splitting function, what is called the QG splitting function. And then you have the final part. And again, this splitting function is a universal function, namely depends only on the fact that we are considering the splitting of a gluon into a quark and an anti-quark, and a linear order. That's a fairly simple expression. So TR is Z square plus 1 minus Z square. TR is normalization of the Gell-Mann matrices. Okay, so we have to include this, and no problem with the, as that doesn't have a corresponding loop contribution, so that's fine. But it does have a 1 over epsilon singularity multiplied by a different splitting function. So that's something we also have to work on. Okay. I guess now is the time to discuss what to do with the splitting functions. So let me summarize what we found so far. So we're looking at the, for instance, the invariant mass distribution. and we computed what is known, the order alpha S correction I usually refer to, so we use some jargon, the next to leading order corrections, okay, because one of the higher. And we can write them as the sigma 0, the leading order cross-section, the point cross-section. And then what do we have? Well, we have integrals. This is the hadron level, so we have the integral over the momentum fraction, Z1, Z2. And here, this one you can write in many different ways. I find it convenient here to also write an integral over the tau hat with the delta function that tells me that Z1, Z2 tau hat is equal to tau. There are many ways of writing. This is, I mean, this integral over Z1 and Z2 are convolutions. So there are many ways you can write them. Just to make sure that you're consistent. And now you can expand out the epsilon dependence and cancel the poles that cancel, and so you leave the one that don't cancel. So you have a sum over all the different pole flavors, each with this fractional electric charge, and then you have the leading order contribution is a delta function in 1 minus tau hat. Okay. Then you have the order alpha S contribution. The order alpha S contribution, well, they have the double pole and the simple pole proportional to delta of 1 minus tau hat. They cancel when we add together the unofficial, and you're left with this pole proportional to the PQQ splitting function. This 1 over epsilon bar. With this I mean the I had in mind doing MS bar, so this is 1 over epsilon, and then these are the ubiquitous constant I always put into MS bar. Okay. Then remember, so if let's go back here, I have this 1 over epsilon pole, but then if I expand the mu square over q square to power epsilon halves, what do I get? I get 1, and then I have an order epsilon term, which multiplies the log of mu square over q square. Now you see I get an interference term, which is finite in epsilon, when I multiply this order epsilon term coming from the expansion of the mu square over q square times the 1 over epsilon. And so this is a feature that always occurs. There is also a term which is proportional to the splitting function and a log of q square over mu square. And now I'm going to identify, I'm going to call this k mu f. Square, and I'm going to put the label mu f so that we remember this stuff. And then you have the finite part. You have a contribution from the real emission. You have a contribution from the visual corrections, and sum together, you get this dQq bar contribution. Okay, and these are multiplied by the splitting function. Q sub 1, f q bar sub 2. And I guess then no one tells you that Z1 belongs to the first is the quark and Z2 is the fraction of the anti-quark. So you should symmetrize this result. But that's, I mean, it's a detail. Okay, so now dQq bar is finite. No poles left. It's a distribution, but there are no poles left. And then there's a contribution coming from a quark and a gluon in the initial state. So this I can write it this way. I is q bar. So that's a charge square. And now what do I have? Well, this contribution with the gluon in the initial state doesn't exist in any order. So it starts at order alpha s. And it's proportional. What do I get? Well, I get the splitting function. And we learn that if there's a pole, then there's also corresponding log. And that's something that will come back over and over again. The singularity, there's an infrared singularity, which appears as a 1/epsilon pole. And together with the singularity, there's also log of some of the ratio of relevant scales in the process. So I apologize, sometimes I write ln, sometimes I write log. I always mean the natural log. And plus the QG of tau hat. And this is multiplied by FG Z1, Fi Z2, and then again I have to symmetrize Z1. Okay, so this is the result I have so far, written in full glory in one side. So how do I get rid of this 1/epsilon? Now the idea is that it's very similar to what we do when we renormalize the theory in the ultraviolet. So you remember essentially the process of normalization exploits the fact that we write down cross sections of matrix elements as a function of the Lagrangian parameters, the bare parameter of the Lagrangian. And we can reabsorb, well, we can redefine our theory so that it is written in terms of renormalized parameters, which are related in some way to the bare parameter of the Lagrangian. And we can do that because the parameters of the Lagrangian are not physical observers, so we can redefine. Now here we can play a similar game. There is something which is not necessarily physically observable, and these are precisely these Parton distribution functions that we have introduced. Okay, a leading order, we interpret them as a probability, but no one tells us that this interpretation survives to the next order. In the same way as if you do a leading order calculation, the mass that appears in the Lagrangian is the mass, but when you include loops, then the parameter which you call mass in the Lagrangian doesn't have to be, is related to the physical mass, but it's not the physical mass. And so what we do is that we're going to follow that route, and we want to define a renormalized Parton distribution function. And now the renormalized Parton distribution function is a function of the momentum fraction, let's call it x, but also is a function of the scale at which we perform the renormalization. How is this defined? Well, a linear order, nothing changes, so it's the bare distribution. And then I want to define it in such a way that it absorbs the 1/epsilon poles. And so it will be something like that. 1/x over 2 pi. This can be a scale of the rotation scale. 1/2 bar. Integral x and 1. And then I have a convolution, pi cube. Let me write it and then we can comment it. Plus PIG plus order squared. Okay, so in the same way I do, I can do renormalization in a similar way. I can do normalization for the parameter in the Lagrangian. I do here a renormalization of the PDFs. Now this is done in a in a very intuitive way. One can be a little bit more rigorous in how you renormalize this. But you can write PDFs as operators and then renormalize them in a way which is a bit more well defined. But the idea is that we just want to we have this freedom of redefining something that which is not. Now you see that one of the feature that is, if this works, one of the features that we're going to have is that our cross-section will be written in terms of this renormalized PDF that naturally acquire dependence of some scale, the factorization scale. And so you might wonder, say, wait a minute, we started by saying that we wanted to have the pattern model because we had Bjorken scaling, so the structure function did not depend on any scale. And now you're putting this back. But indeed, Bjorken scaling is something which is indeed broken. So if you do more precise experiments, you see that indeed the structure function do acquire a logarithmic dependence on the scale of the process, and this dependence is fully determined. It's in full agreement with what we're going to do in the next few minutes. Okay, so the fact that we are putting back a dependence on the scale can be checked against the experimental data that it's actually supported by physical evidence.
Sorry, I have a quick question.
Absolutely, go on.
Just in red in the logarithm, I just can't read what you wrote.
Oh, F. I call it, so yeah. Before it was just written as mu, but really this is the mu F, the factorization scale.
I mean in red.
In red.
Yeah, 1 over epsilon bar, sorry.
Okay, yeah. So I just said what I meant by 1 over epsilon bar. I mean 1 over epsilon plus this log of 4 pi e to the minus Euler gamma.
Euler gamma.
You're right. This is written in a horrific way. Sorry about that. I mean, just to define the symbol, but it's when you do MS bar subtraction, you always subtract the poles and this constant log of 4 pi.
Yeah. Thank you very much. Sorry.
No. Okay. So now
I also have a question.
Go on, please.
Yeah, but when we define the Bjorken scaling, we use this structure of constant functions. I don't know how to call them. But now we are talking about pattern distribution functions. So, are these two related?
Yes. So yeah, okay. I guess I skipped a few steps here. So when you do the calculation for deep analysis capturing, what you find is that the structure functions are essentially proportional to the pattern distribution functions with some coefficient that you can calculate. And so that's the way we obtain that the structure functions are. So in the pattern model, the PDFs do not depend on Q square. And as a consequence, the structure function, which in the pattern model are proportional to the PDFs, also do not depend on Q square. And that's sort of like the way we obtain Bjorken scaling from the pattern model. Now, if you insert back a mu square dependence in the PDFs, this will feed back to a mu square dependence of the structure function.
Okay, thanks.
I'll try to. There's a beautiful. Well, let me comment later on this. Okay, so now what should we do? Well, we should solve this equation for Fi perturbatively and substitute in this Fi into our NLO cross-section and expand it to order alpha s. And you see that if you get, you'll find an expression of, you'll find that you can express the NLO cross-section in terms of the renormalized PDFs. And these are defined in such a way that indeed this contribution cancel all the unwanted pole. By the way, this is a usual trick that we're doing perturbative normalization. So here I can really write already renormalized, because the difference between the renormalized and the non-renormalized is an order alpha s. And so here, because I already have an order alpha s in front of the integral, I can at this order, it doesn't matter whether here I write renormalized there. Okay. Now I have in my notes the calculation, but I don't want to spend too much time on it. But it's an interesting exercise to show this actually works. So you have to work a little bit with all these convolutions and to see that the cancellation actually happens. I leave it to you as an exercise, but it's actually on the notes, so you can also see. Okay, so let's imagine that we do that, but the procedure is clear. So you solve here for the Fi, you substitute in the local section. So at the end of the day, you only have a result which is expressed in terms of the renormalized PDF. Okay, so let's write it. I write it in with the same structure I wrote before, so nothing changes here. Okay, and now let me write it in a more compact form. So I'm going to write a sum over all possible patterns I and j. So I and j could be quarks or gluons. Okay, so what is the structure of the leading order? Well, a leading order, I have to pick a quark and an antiquark. And then the kinematics is constrained to be delta 1 minus tau hat. Then I have the alpha s over pi correction, let me write it this way. And I'm going to change, like these are usually referred to as coefficient function. These are related to this d, which I've written, but also contain this log of q squared over mu f contribution. So that's why I changed the name. I just call them C. And these are fairly common names. These are called coefficient functions. What do they depend on? They are distributions, and in tau, they depend on tau hat. They can depend on the renormalization scale. And if I write there the normalization scale, then I mean that alpha s is evaluated at the renormalization scale. Okay, and then they can depend, or they do depend, on the factorization scale. And let me put here a 1, meaning that this is the first order, this is the coefficient of the first order in alpha s. Okay, and this multiplies f renormalized I z1 in f squared f renormalized j z2. They are supposed to be in pink. And this sum correctly accounts for all possible combinations. Plus order. Okay, so now we have now we're done, in a sense that we found we're able to define a calculation scheme which gives us finite finite corrections and x unit. So d sigma dq squared NLO is something that is finite, and we can compare to experiments. There's still one thing that bothers me a little bit, and is well, what do I take as a normalized PDF, and how do I interpret this mu f dependence? So if you remember, if you go back to the picture that I wrote when we started this calculation, I'm just going to show it to you, and then which was the picture of this factorization theorem. And you see that I have this my proton coming in, and there are some green, which in my color code is non-perturbative, and then they sort of like become perturbative in red. And then I drew this line with this mu f. Now I can make a little bit more sense of that drawing, if I say so. So here I have my proton, and my proton comes with in the pattern model, my proton, well, in perturbative QCD, the proton is really represented by a renormalized PDF. And the renormalized PDF is renormalized, which means that accounts also for some radiation. some of this radiation, it's put into the renormalized PDF by this operation here. Some other radiation instead is put into the coefficient function. Okay, the coefficient function receives an order of phase contribution, which means that some radiation is contributing to this expression. Other radiation instead, I reshuffle into the renormalized PDF. Why do I make this distinction? Well, I make this distinction precisely at the scale μf. So we can interpret the scale μf, the factorization scale μf, as the point at which we separate what we consider the radiation that we put into the renormalized PDFs and the radiation that goes into the hard interaction. In some sense, that's something that the first person that told me QCD said. μf represents where we decide the proton begins. Radiation which is harder than μf goes into the radiation above μf goes into the hard interaction. Radiation below μf goes into the renormalized PDF, which for me, phenomenologist, is the proton. Okay, so that's a sort of like my physical interpretation of that. You can ask, like, do I have to? Am I forced to pick μf to be a particular value, to be in some sort of range? Well, not necessarily, and we'll come back to this in a second. The other thing that you can ask is that, is this way of separating things universal? And the answer is no. In a sense, in the following sense. Here we decided to define renormalized PDF as the bare PDF plus or minus the pole contribution. Of course, if you want to have a finite cross-section, this is the minimal thing you have to do. You have to take all the poles, the collinear poles, and put them into the PDFs. And indeed, this is called the minimal subtraction scheme, because that's minimally, that's what you have to do. But you can do more, or you can do different things. You could choose to reabsorb all the order alpha correction into the PDFs. Indeed, in deep analysis scattering, this is sometimes done and gives rise to what is known as the DAS scheme. And so the distinction between renormalized PDF and coefficient function, we say something that is scheme dependent. Okay, so we must reabsorb the poles into the PDFs, but what we do with the finite part is really up to us. And so really beyond leading order, PDFs, they lose this interpretation probability also because they're no longer physically observable. They depend on the factorization, or the choice that you make. So in the technical word would be they depend on the factorization scheme you choose. So whenever you pick up a PDF, nowadays, people imply that this is a PDF defined in MS bar. But that's not like the only choice. You can define different schemes which are more suited for your calculation. And these PDFs will differ in a controlled way from the MS bar PDF that we usually employ. One thing that, sort of like instead we would like to say is that, well, okay, let me say two things. That if you always choose the same, for all processes, the same factorization scheme, then renormalized PDFs are universal in the same sense as bare PDF. So you can use the renormalized, once you fix the factorization scheme, you can use the same PDF they use for deep inelastic processes. You can use them for Dralian, you can use them for risk production, and so on and so forth. So universality is maintained once you fix the factorization scheme. The other question I wanted to address is the following. How do I choose μf? Or am I forced to choose μf in a particular way? The answer is no. μf is in the same way that the renormalization scheme, when you do ultraviolet normalization, is a free parameter, it's a perturbative scale which is not fixed by your calculation. In the same way, μf is an arbitrary parameter. In some sense, you can decide where the proton starts and where the high interaction side. And so your physical observable, d sigma dq squared, should not depend on this choice. And so we translate this into this type of equation. So if we take the derivative, we take the log derivative for convenience of our physical observable. Our physical observable is this one. The physical observable must not depend on the choice of mu f. More precisely, if you compute the physical observable at order alpha s to power n, then the dependence of the physical observable on mu f should be of order alpha s n plus 1. Namely, remember, we're still doing perturbation theory, so 0 for us means something which is high order. Okay? Now you do. So this is the key point. So if it's not clear, I can definitely repeat. But the idea is that we can demand that perturbatively our physical observable, our physical cross-section does not depend on mu f. Then you ask yourself, what is the mu f dependence in my expression? Well, there's a mu f dependence in the coefficient function, and there's a mu f dependence in the renormalized PDFs. If the product of the two should not depend on mu f, it means that the dependence on mu f of the coefficient function must cancel the dependence on mu f of the renormalized PDFs. Order by order perturbation. But we sort of know, even if we say, okay, the renormalized PDFs are non-perturbative objects, I don't know what to deal with them. Let's look at the perturbative side. Well, what is the mu f derivative of Cij? Well, remember, C was built of D, which was mu f independent, and this log of q squared over mu f. And so the log derivative with respect to mu f of Cij must be proportional to my splitting function. At least the order alpha s becomes really more complicated than pi. So if I want the mu f dependence to cancel, then the mu f dependence of Cij should cancel the mu f dependence of the renormalized PDF. But the mu f dependence of Cij is completely determined by the splitting function, which means that also the mu f dependence of the PDF is completely determined by the entirely by the splitting function. Okay, so this leads to a set of equations which are among the most famous and important in QCD and Collider phenomenology, which are the equation written down first for QED by the Russians, and then famously in a beautiful paper by Antitled Chapter for the full case of QCD. So they go under the name of Diegler equations. Docisser, Glebov, Lipatov, Antitled Chapter. And I can summarize them right now. So they tell us how the renormalized PDF depend depend on what. Now I'm taking only one flavor of quark. You should have, like, if you have more flavors of quark, then FQ itself it's an array. Now the mu f dependence of the PDF, it's equal to the mu f dependence of the coefficient function. So it's alpha s over pi mu f squared, and then there's a convolution integral z over z. And then there's a matrix. I'll write the matrix in a second. And the matrix acts on FQ of Z square and FG of Z. Sorry, these are always renormalized PDF. What are the entries of the matrices? Well, these are the splitting function. Two of them we saw already. And then you also have these ones. So these are the arbitrarily placed splitting functions at leading order. You see that I've written them as an alpha s times the splitting function. You can generalize them to any order in perturbation theory, but that's enough for our purposes. And what are the splitting functions? Well, they represent, you know, the name says it, they represent the splittings. PQQ, we already seen it. It represents this splitting. PGQ, we saw it representing this splitting. Old space-like splitting. And then you have PGQ. Oops. And then PGG. You can write analogous one for time-like splittings, but here I always have in mind that these are initial state radiation. So what do we learn? PDFs and renormalized PDF in general. Well, and so I'm gonna, from now on, I'm gonna drop the, I always mean renormalized PDF. I'm gonna just drop it. PDFs are non-perturbative objects. They can be defined. PDFs are non-perturbative objects which I can use to absorb collinear singularities of my coefficient functions. They are non-perturbative. However, through the process of renormalization, they acquire a dependence on the scale μf. This dependence on the scale μf, this evolution in μf, we say, is determined by perturbative QCD. Because the evolution kernel, this matrix of the splitting functions, is something that we compute order by order in alpha s. Here I've written the first order in alpha s, and one can write down the second order correction, and then on to 3 loops. This also gives us a strategy on how to compute, how to fit PDFs, because we can do experiments at different energies. So the PDFs will enter this description of the data different energy, but using deep evolution, we can put them, we can bring them to all the same scale and fit the initial condition. So another way of saying is that the initial condition of the PDFs is not perturbative, but its evolution in UF, it's perturbative. So, okay, I want to say one more thing about PDFs. So the factorization theorem that we wrote down to order alpha s can be generalized to I orders. Okay, and in general, the factorization theorem in its full glory, we would write it as, say, for instance, the sigma hat tau and q square, we'll write as sigma 0, sum of I and j, a coefficient function that now contains I order corrections, c over z, tau over z, mu r square over q square, mu f square over q square, and alpha s r square. Convoluted, and this convolution is over Z1 and Z2 with renormalized PDFs. Okay, so this is the all order version of what we've written. so far. And the C admits a perturbative expansion in alpha s. So when you do perturbative calculation of one loop or two loops or beyond, you'll find ultraviolet divergences, then you absorb with the normal procedure, and that's why you get a dependence on mu. And you will find soft and collinear divergences. Some of them will cancel. Some collinear divergences will have to be order by order absorbed into the PDFs. Now, let's take the contribution. So Cij admits an expansion so there will be a C0 plus alpha s C1 ij plus alpha s squared C2, and so on and so forth. Now, let's look first at the mu r dependence. Each perturbative coefficient, Ci, will contain logs of mu r over q squared. Okay, so Ci will contain so alpha I, alpha s to power I Ci. It will contain some alpha s times log of q squared over mu squared to some power. Let's say the most average. Now, that's an argument that you may be heard in renormalization. Then you can use the renormalization group to evaluate the coupling, the scale of the coupling. So P to choose mu r to be equal or close to the hard scale of the process Q. Okay, so using the renormalization group, you can effectively choose alpha s of q squared. And if you do so, if you choose mu r equal to square, you see that you don't have any logarithmic correction in the coefficient function because the log of 1 is 0. And all the logs, we say, are accounted for by the running coupling. If I say something that you never heard, right, please stop. Okay, so you can use the running coupling you can use the renormalization group to evaluate the coefficient function, mu r in the coefficient function, and mu r in the explicit alpha s dependence, so that there is no log left in the coefficient function because you have the log of 1. And the price you pay, or what you have to do is that you also have to evaluate the coupling at the scale q squared, at the physical scale q squared. And what is the relation between the coupling at q squared and the coupling at mu squared? Well, it's given by this formula which I just written. Let's look at this formula in a different way. I can expand it in powers of alpha s. And so this will be an alpha s times the sum k 0 to infinity, alpha s to k, beta naught to k, log k, q squared over mu squared. So one way of describing this phenomenon is to say that by choosing mu r equals q squared, what we do is that we resum in the running coupling all the potentially large logarithmic correction q squared over mu r squared. Okay, by using the running coupling, what we are effectively doing is that we are resumming to all orders in perturbation theory. Resumming maybe is not the right word at this point. We are accounting for to all orders in perturbation theory contribution of the form alpha s beta naught log q squared over mu squared some power. Okay, that's what the renormalization group does. By defining a running coupling, you are effectively taking these potentially large logarithmic correction from the coefficient function, put them in the running coupling in such a way that you're accounting for them to all orders in perturbation theory. You see that the sum goes from 0 to infinity. You have all orders accounted for. Now, something very similar happens for Diglab evolution. By choosing the pattern distribution functions, which depends on mu f, by choosing the factorization scale mu f to be of the order of the hard scale of the process, we get rid of the mu f dependence in the coefficient function, and we essentially resum all the logarithmic corrections in the Altrardi Parisi by the Altrardi Parisi evolution. Now, in order to see how this works in practice, I'll do this in the last 5 minutes before the break. We have to try and solve D-gap evolution. Now, D-gap evolution is mostly solved in a conjugate space, which is called the Manning space. So what Manning space does for you? Well, if I have a function, f of x, then the Manning transform on this function is defined as the integral between 0 and 1 dx x minus 1 fx. Now, a crucial property of Manning transformation, which I invite you to show, is that if I have a convolution product, then in Manning space, this convolution turns into an ordinary product. And so D-gap evolution in Manning space becomes Q. You see that the convolution are turning into ordinary products. What are these gamma? These gamma are famous, so we give them a name. They're called the anomalous dimensions. And the name is related to the fact that in deep inelastic scattering, you can use the OP to describe this. So these are the leading order anomalous dimensions. Okay, but now we are essentially done because we can solve this equation in a rather simple. Well, we can solve this equation so that I don't it doesn't take me another hour to solve it. Let me make two further assumptions. Let me solve it only for the quark. Let's assume that we live in a world where are no glues. If you're very picky, you can diagonalize the matrix and solve the equation for the two eigenvalues, so they are the couple. But let's solve it just for one flavor for the quarks. Then you have mu square, the mu square. Let's call it Q, and this would be alpha s mu square over 2 gamma n Q. Okay, we can solve this by separating the variables. So what we have is that we have dq over q equals to alpha s of mu square over 2 pi d mu square. So this gives you the log of, let me put the dependence now. So let's say I integrated between q of n n mu f square and q of n and q square. I don't know why I call it q, let's call it f. And this must be equal to the integral between mu s square and q square of d mu square over mu square alpha s mu square. And so the solution to this equation, the solution is f of n f of n square. Well, this is the f at the initial scale, f, times an evolution factor, and this evolution factor is the integral between mu f square and q square. So here there was a gamma n, which I forgot. Alpha s q square, 2 pi, gamma n. Now this integral can be done, so you can pick alpha s of mu square as the alpha expression of alpha s in one loop. You can do it as an exercise, but let's imagine for a second that alpha s does not depend on mu square, so we can take it out of the integral. So we do the fixed coupling approximation. And now everyone can do this integral because the if alpha s goes out, then this is the integral of 1 over mu square. So this gives you alpha s over 2 pi gamma n log of q square. And you see, and that's really stop here, that indeed the solution, by evolving the PDF from mu f to q square, you are resumming, so you are counting for all this in perturbation theory, all the contributions of the type alpha s to the k, gamma n to the k, log k, q square over mu square. Through all orders in perturbation theory. Okay, so by solving the gap evolution, we are resumming all collinear logs to all order perturbation theory. If we solve the leading order the gap evolution, we are resumming what are these logs, which are known as leading logs. If we were to solve the next linear order the gap evolution, then we would resum also next leading logs, and so on and so forth. You see another feature of this solution is that this can also be written in this way. That's q square over mu f square, to which power alpha s 2 pi gamma n. Hence the name anomalous dimension. Okay, I went over time, so I think you all deserve a break. And I guess we can reconvene in, I don't know, 10 minutes. What do you say?
Yeah, perfect. Thanks.
Okay, sorry for going over time, but I wanted to finish this this part.
You mean by 1 minute, or?
Okay, well, that's so. It felt longer, but okay. Bye-bye.
Bye-bye. Simone, I think we can start again. Right?
Okay. Okay. Yeah, sure. Welcome back, everyone. So, recap so far. So what we tried to do in the past 3 hours was essentially to calculate and show how we can make sense of perturbative QCD calculation in the context of a proton-proton scattering process, in particular the Derrida process. And we did that for inclusive cross-section. So crucially, we said, well, we only care about the muon pair, and we sum over all possible radiation. And this allowed us to sum the real and virtual corrections, and so to cancel some of the emerging infrared singularities. Now, what we learned so far? Well, we learned that there could be ultraviolet divergences that we need to deal with the renormalization. And then we can have these infrared singularities. Now, soft singularities, we actually managed, we've seen that they cancel. Soft singularities where this term, the epsilon poles proportional to the delta function. Actually, this we didn't discuss it, but it can be shown that if you have a process with final state singularities, for instance, a plus A minus into hadrons, then all soft and collinear singularities would cancel. The only type of singularity that doesn't cancel when you sum real and virtual together in this context are these initial state collinear singularities, which are proportional to the splitting factor. And for those, they have to be absorbed into the pattern splitting factors. What they leave behind are collinear logs, these logs of q square or mu square, which can be resummed by essentially exploiting the Kepler function. So this is sort of the Bouvier sense. However, one of the things I said at the very beginning was that one thing we like about collider experiments is that we have many final states, and we can look, measure, compute many different distributions. So really, collider phenomenology should be a little bit more than inclusive observables, and that's what we'll try to address in the second part of these lectures. So now we start lecture 3, so I'm kind of 1 hour behind, so I'll try to make up time maybe tomorrow. In this lecture 3, we want to discuss resummation for more exclusive observables. So in order to do so, we have to do 2 things. First, we want to introduce the concept, go back and look at, again, what happens at matrix segments in the soft and collinear limit, and discuss about the important property, which is called ISC safety. And that's probably what we're going to achieve in the next hour. And then tomorrow, we'll look at a specific example, which is a classical observable, which is the transmomentum distribution of the Z pose. Okay. So another way of stating what we learned so far is the following. Let's consider a more generic process, like a process which has, if we are computing it in perturbation theory, it's a generic scattering process which has n partons at linear order. The specific one we looked at is the Drell-Yan process, which has n partons in the final state. And final state partons. So Drell-Yan has 0 partons in the final state. What can be done, and people actually know how to do this in a fairly automated way, is that we can calculate all these processes at next linear order. We can actually do better, but let's stick with next linear order. And generically, this will be the linear order cross-section plus the real contribution at next linear order plus the virtual correction. And what does this guys look like? Well, the linear order cross-section will be the integral over the n parton phase space. Okay, and then plus what we're going to have. Well, we're going to have the real matrix segment square, and this will be integrated over the n plus 1 partons final state, because the real emission has 1 more parton. If you think about Drell-Yan, you have 0 partons at the linear order, you have 1 parton next linear. And then you also have to integrate the virtual corrections. And the virtual correction, they live in the same phase space as the bond. Now, what happened is that if you take the limit where this n plus 1 partons is soft or collinear, the R term and the V term are separate version, but their sum is finite after UV normalization and PF normalization. So these are self-divergent, but some is finite after UV and PDF renormalization. Okay. Actually, here one can open like a bigger side, but we're not going to go into that. To say what is the most efficient way of computing these intervals? At the end of the day, we probably want to integrate things numerically. So a lot of like the effort that goes into this type of problems is to try to figure out a way of moving the singularity from one interval to the other one, so that the resulting integrand is finite and we can integrate in general. This goes under the name of like the problems of finding the correct subtraction scheme. This is being fully solved in more than one way at NLO. It's still like there's a lot of work in progress and next. Okay, so that's for the inclusive cross section. But we said that we want to measure something a little bit more differential. So let's imagine that we want to measure an observable O. Okay, and O will be a function of the final state momentum. I'm going to call them QI now. What would be this O? Well, this O, it's a measurement function that can contain, for instance, delta function, theta function. So for instance, I can say I want to measure the invariant mass of certain particle clusters together, or I want to measure only the transit momentum of all those particles which are above a certain cut. So it could be like complicated as you want. Okay, but this measurement O defines a set of measurement functions, and of course this measurement O for us theorists, the input of these measurement functions, these are pattern moments. For an experimentalist, this will be hadron moment or particle moment. Okay, so how do I? What I'm going to write? Well, let me cheat a little bit. Well, if I want to do this, I want to find the distribution of this cross section as a function of this measurement function, or as a function of this observable O. What do I have to do? Well, I have to insert this measurement function. Here, a leading order of the measurement function will take as inputs the final state momentum. So I'm going to indicate it with ON. And the same will be true for the virtual projections. They live in the same phase space of the measurement function. However, the measurement function I have to use for the real emission, well, this will take n+1 partons as the arc. Okay, you see that now I would like the cancellation between real and virtual to continue in the same way. Okay, so after I've done UV and PDF memorization, I still want to have real and virtual, this time weighted by these measurement functions, and I would like, the answer to be still fine. So the cancellation of these, we call them IRC singularity, infrared and continuous singularity, still holds only if the measurement function for the n+1 final state phase space reduces to the measurement function for the n final state when either two particles become collinear, we know there's a collinear singularity when two particles are close and equal, or when one pattern becomes soft. So when one pattern, say, becomes soft, then I potentially have a collinear singularity. This will cancel between real and virtual if, in that limit, the two measurement functions act in the same way. And this is what I mean by that the measurement function on the n+1 phase space should reduce to the measurement function, the n phase space. This request, which seems rather obvious, is one of the most important requests that we're going to make about observables from a theoretical point of view. An observable that respects this property is called an ISC safe observable. So in general, if I have an observable which depends on the final state momenta, well, I want that if two momenta become collinear to each other, then the observable should only depend on the sum of these two momenta. This way, the observable will be collinear safe. If I have my observable which depends on all of these four momenta, Q1 to Qn, then if one of the momenta becomes soft, then the observable should not depend on this one. This definition of infrared and collinear safety goes back to the work by Sterman and Weinberg, and is sometimes referred to as the Sterman-Weinberg definition of ISC safety. So if two particles become collinear, then the observable should only depend on the sum of the momenta of these two particles. If one particle becomes soft, the observable should be independent on this. Okay. There are other possible definitions. For instance, a couple of years ago, there was a very nice paper by the MIT group, so Jesse Taylor and his two students at the time, called Patrick Miska and Eric Metodio, where they tried to come up with different definitions for ISC safety, and they have a very nice geometrical interpretation of ISC safety. So if you're curious, I'll post the paper on the Slack later today, but it's a very nice alternative idea. Okay, so from the point of view, well, from the point of view of calculating things, it is rather obvious why we want ISC safety, because otherwise our cross-section will be infinity. Okay, and that's not, most of the time, it's not a good answer for a calculation. Well, but you can say, well, I mean, we know that QCD, perturbative QCD stops to make sense in the soft and collinear limit, because if you're sensed to a very low scale, then your coupling becomes non-perturbative, and like you're talking about quarks and gluons, but you really should be talking about pions. That is true. I guess one way of stating, so from the perturbative viewpoint, we need ISC safety to get finite cross-section. From a sort of like phenomenological viewpoint, we want ISC safety because we want to build observables which are not too sensitive on the non-perturbative. They don't depend too much on the non-perturbative aspects of QC. So for ISC safe observable, it is, you can show these corrections to the path-to-path duality, the naive sense, are genuine power corrections. So they scale as some lambda QCD divided by Q. If the observable is not ISC safe, then this correction, this non-perturbative correction, could be of order 1. So let's make some examples. So if you try to count the number of particles, which is often referred to as particle multiplicity, which is a very useful experimental concept, then this observable is not ISC safe. Because imagine you have a collinear splitting. A collinear splitting increases the number of your particles, because you go from 1 to 2. And that's true regardless of light close there. And so particle multiplicity is not an ISC safe observable. We cannot compute particle multiplicity in perturbation theory. We can model it with non-perturbative correction, but this non-perturbative correction will be of order 1. On the other hand, for instance, the let's say the invariant mass of a QCD system. So I have a QCD system with momenta Q1, Q2, up to Qn, and I compute the invariant mass of the system. This is instead ISC safe. Why is the case? Well, of course, clearly, let's say the Q2 becomes very soft, then the mass does not depend on Q2 in a relevant way. Let's say Q1 and Q2 becomes close in angle, then the mass, I mean, this observable is linear in the momenta, so the mass will only depend on the sum. So the binary mass distribution is instead an ISC safe observer. In the rest of my discussion, I'll mostly concentrate on ISC safe observers because I want to be able to calculate things. Now, sometimes we have to give up ISC safety. It's better not to, from the theory point, but sometimes experimentally we have to do so, and so we can try and deal with the non-perturbative corrections, which can be large. For instance, this particle multiplicity is a very powerful discriminator that is in searches, and so okay, fine, we give up calculating this thing with precision, but we can still use it as a phenomenological tool. Now, just a curiosity. We can actually use the concept of a C safety sort of like to give another explanation of why initial state collinear singularities give us, they don't cancel in the sum. So I mentioned that we have general theorem, which are essentially the Kinoshita-Lee-Neuber theorem, but which states that if we sum inclusively over all possible real and virtual radiation in the soft and collinear limit, all singularities should cancel. However, we explicitly seen that when we calculate Partonic cross-sections, we encounter uncancelled collinear singularities. Now, if you think about it, the concept of Partonic cross-section, it is not an ISC safe concept. And why is this the case? Well, the Partonic cross-section, in the way we defined it, sigma hat, depends on Z times the incoming momentum of the incoming proton. Okay, let's imagine now this situation. So we have incoming proton, we have an emission. This takes away 1 minus Z, this is Z, and this is theta. Now, the way we define Partonic cross-section is that regardless of how collinear this gluon is, the momentum that entered the ion interaction is always Z times P. And so even if is never P itself, even if the gluon and the quark will go very collinear, you don't take the sum of ZP plus 1 minus ZP, which will give you P. Okay, but you always have Z. So the way the pattern model is built is not ISC safe, but that's the best way we can do. And it's not like, it's not the end of the world. We use PDFs, and PDFs are an order 1 corrections. So the non-perturbative information is an order 1 correction, which we need to fit from the data. In another way, we're not fully inclusive because we demand the protons in the initial state, while we can be fully inclusive in the final state because we don't have to specify which atoms we want to have in the final state. If we are to specify atoms in the final state, well, we will encounter the same problem, and we have to define fragmentation function to absorb collinear singularities. Okay, so as I mentioned in the discussion we're going to have today and tomorrow, we're going to concentrate on ISC safe observers. And so for this observer, we can use perturbation theory. And we are okay. So we know that we use perturbation theory, and singularities will cancel when we sum real and virtual corrections. But another question, the second question is, but is perturbation theory going to be reliable? One thing said that we can use it because we get something finite. But is what we get rubbish, or can we use it to compare to data? In other words, we've already seen that even if you have cancellation of singularities, or if you reabsorb singularities, you can have left in the coefficient functions, so in our cross-section, contributions which are finite, but potentially large. And typically, these are potentially large because these are logs of the ratio of 2 scales. So this is the problem we're going to try and discuss now. So we use perturbation theory to compute distribution for ISC safe observers, but then we can ask, but also we have to worry about the fact that this distribution, for this distribution, perturbation theory may not be very reliable. And in particular, we expect the perturbation theory may get into trouble if if the observer that we are looking at lives in the soft or collinear region. So for this reason, what I want to do next is sort of like to look at soft and collinear singularities in a slightly different way compared to what we've done so far. So yesterday, what we did is that we wrote down the full matrix element, and then we took the soft and collinear element. And if you want, we did the loop integral, and then we recognized the poles. Now we want to go the other way around. We want to take the matrix element and try to see if we can, by inspection, understand what is going to be the structure in the limit where two particles become collinear or one particle becomes soft. So let's start with QCD matrix element in the collinear limit. Okay, so the picture is always the same that we had before. So we have our hard interaction. We have two particles coming in, which we label P1 and P2, and then we have well, I said we have our. If we think about the Z, we still have our plus P minus, but we don't really care about it. And then we have n partons in the final state. Let me call it, let me relabel Q1, Q2, Q3, Qn. Okay, so they're all treated. Now, what happens in the collinear limit? So what happens when two partons become close enough? So let's say that one of the parton emits a photon with momentum k. Sorry, a gluon with momentum k. I'm interested in the case where this n+1 parton becomes. No, sorry. Forget to say that. I don't want to spoil my notes. So let me write this as P1. P2 and then n partons in the final state. Otherwise, I need to change the notation limits. I apologize for this. Okay. So what happens, and we kind of seen already, is that the matrix element square for n+1 partons, matrix element times the phase space +1 partons in the limit where Qi and K becomes collinear to Qi. That is the limit where Qi plus K, the invariant mass, goes to 0. In this limit, the matrix element factorizes. The matrix element square factorizes into the matrix element for n partons with this phase space times alpha s over pi, and then I have the phase space for the emission in the collinear limit, the theta square, where the z p ij. And ij because, I mean, in this case will be ij because it could be the emission of a gluon of a gluon of a quark, so on and so forth. What are the z and this angle? Well, if I have my Qi, splitting, then the angle is really the opening angle between the two. And in the collinear limit, I can assign the momentum fraction to each of the splitters. Now, this is done, I mean, it's purely a matter of convention, but typically, if you're dealing with a final state radiation, as I'm doing here, so the emission, if you want, is time-like. The propagator that goes on shell is time-like. Then one usually said the gluon as Z, and this is 1 minus Z. If instead you're doing initial state radiation, So let's say the gluon is emitted from one of the incoming leg, and so the propagator that goes to 0 is space-like, then one usually calls this so qi 1 minus z. So just to add confusion, so if you look at the literature and in say for Dirac evolution, for initial state evolution, then the limit in which the emitted gluon is soft is z goes to 1. If you instead look at like most of the papers with final state, which talk about final state radiation, the emission in which the limit in which the gluon is soft is set to 0. Okay, so that's unfortunate, but we need to every time we need to understand what is meant. So this is for one emission. What is interesting is that we can actually iterate this. So if you have emissions from different legs in the collinear limit, well, they factorize in a trivial way. What is more interesting is that if you have multiple emissions from the initial leg in the collinear limit, all in the collinear limit, then you still have factorization. Well, you have a convolution of all the splitting currents, which can be diagonalized if you take a Manning transform. So if you have two emissions from one leg, then and you go to Manning space, then you really can write this as the product of the anomalous dimension. Okay. Now, what is interesting is that some of these splitting functions, they're also enhanced in the soft limit. So, for instance, we took PQQ has this form. This was for a space-like splitting, and so the soft limit was where z goes to 1. So for initial state radiation, and these, then the phase space of the emission will be the color factor, which lives in the splitting function, theta square dz 1 minus z. If instead you look at a because this is initial state and final state of here. If you look at, say, a time-like splitting, then usually we said the soft limit is indicated by z goes to 0, and then the collinear emission looks like d theta square plus theta square z plus z. So you see, there's a collinear singularity, which I written as theta goes to 0. And then the splitting function itself may have a soft singularity. So if I take both the theta to 0 limit and the z to 1 or z to 0 limit according to my kinematics, then I'm looking at the soft and collinear limit. So people talk about the strict collinear limit where emissions are close in angle. So I take only the leading behavior in one of theta, but I'm not making any assumption on the energy fraction or the momentum fraction z. Or I can take the soft and collinear limit where I make two assumptions. And this is the most singular limit I can think of because I demand my emission to be soft and collinear.
Can I ask for a clarification?
Sure.
I mean, what frame is this occurring in? Because presumably the opening angle is, Lorentz frame dependent. So are you working exclusively in a lab frame here, or?
So that's why I was excellent question. Thank you. So the way we should phrase it is in terms of Lorentz invariant, and so that's why I said in here maybe I said it like be quick. Here the limit I'm taking is the limit where this invariant the propagator goes. So this invariant mass goes to 0. That's the proper way of defining the limit. It's in a Lorentz invariant way. Then I can say, okay, how do I interpret this? Well, I can, if you want, sit in the frame either of the decaying particle, but if it's strictly on shell, it wouldn't be a frame. And then I look at the opening angle. If you're looking at initial state emission, then the natural frame will be the lab frame. So design, if you look in an initial state radiation, then this angle really will be the angle between the emission and the beams. If you look at the final state, then this angle is essentially measured with respect to the jet axis, if you want, of the direction of the emitter. But you can phrase it in a way that really the singularity arises because you are you have a propagator that goes on its mass.
Okay, thanks.
I guess if you usually these angular energy are defined with respect to an emitter, but you're correct. So you have to define. Okay, one thing I want to say now, but we're going to use it at the very end of the course. You see that if you have an emission in the soft and collinear limit, the phase space looks like d theta square. The phase space for this emission is d theta square over theta square, dz over z. So this emission. So if you plot this phase space as log of 1 over theta square, log 1 over z, okay, in this plane, then the emission has equal probability. In the probability for the emission is uniform. The probability of a soft and collinear emission is uniform in this plane, which means that if you have many emission, all soft and collinear, the probability that they end up in a given area of this plane, this plane, is proportional to the action area of the plane. Okay, so we can think of like populate this plane by exploiting the fact that for a given the area we are populating is proportional to the probability. At this moment, it's just an information. We're going to exploit this towards the end of this lecture. What I want to say more about collinear factorization, well, you see, I wrote collinear factorization for matrix element square. So really, I can think about collinear factorization as a factorization of probability. And this comes together with a sort of like semi-classical way of thinking. So I can really think of like probability of emitting 2 partons is the product of the probability of one, then no emission probability, then emitting another. And this idea of essentially we can exploit this almost classical behavior of matrix element square in the collinear limit to build algorithms that allows to simulate events. And this is essentially the core of like what I call Monte Carlo pattern shower event generators. So the idea is that one can show that this chain of subsequent collinear emission is essentially a Markovian process, and we can build this way. Essentially, we can simulate events at in proton-proton collisions. Okay. So in some sense, collinear emissions are easy. They are almost classical. What is tough instead is looking at soft emission, which are not necessarily collinear. Now, why is the case? Well, let's try and evaluate what happens in the soft but not necessarily collinear limit. So let me take for again my example. I have my hard process. I have maybe my Z that decays into plus and minus, which I'm going to ignore. And then I have my momentum. Now, yes, here is easier it's more convenient to label Q1, Q2, Q3, Qi. Okay, now let me take my momentum Qi, and I'm going to do this in the case of final state radiation, but it's not difficult to also look at the initial state case. Okay, let's write down the matrix element, where the gluon is emitted from parton QI. Well, here I'll have epsilon mu star k. I'm just going to write down the matrix element. Y. Then I have the vertex. Yes, gamma mu. TA, and I put an index A because it refers to parton A. This could be parton I. I could be a quark or a gluon, so that's why I need to label it a different way. Let's imagine it's a quark. I propagator K plus epsilon, and then I have a reduced matrix element, which is essentially anything, all of this. Now let's take the soft limit. In the soft limit, K is much smaller than Qi, all components. And so if I do this limit, then what I'm going to get, epsilon star, K, U bar, Q1, Qi, sorry, minus I, GS, gamma, mu, TAI. Now we look at the numerator, where in the numerator I can drop K slash because K is much less than Qi. So in the numerator, I have I Qi slash divided by, what do I have in the denominator? Well, Q squared is 0 because the gluon is on shell. Qi squared is 0, and so I'm only left with 2 K dot Qi plus I. Now I can rearrange these essentially using the Dirac. I can write down. I can use the commutation relation between gamma mu and Q slash, which is a gamma mu slash, to swap the two matrices, and I can use then the Dirac equation so that I can cancel one term, because if I swap gamma mu and Q slash, then when Q slash acts on U bar, I get 0. And so the only term that survives by using the Dirac equation is epsilon mu. I guess I need to write down this formula, and then we're done for today. Divided by 2 Qi dot K plus I epsilon. And then I have U bar, Qi, TA, number. Here I can divide out by 2, and then I redefine epsilon to be epsilon over 2. And you see that I achieved some sort of factorization, because I can write the matrix in the soft limit, the matrix element for n plus 1 partons reduces to a matrix element which knows about n partons, color factor, color matrices, and U bar. And then I have this factor which tells me about the momentum of the hard parton divided by this Qi dot K. And this is called the icon factor. Now, if we were doing QED, this could have been a bit even more powerful, because I wouldn't have this TA, and so I could already recognize U bar, M bar to be the matrix element for n partons. And now this does not happen in QCD, because the matrix element remains trapped in this structure, and that's essentially the origin of the difficulty in treating soft gluons with respect to soft photons. Now, I think I probably should stop here for today. So what we're gonna do tomorrow is we'll try to push we'll try to understand better how we can make sense of the soft approximation, despite the fact that we don't have a complete factorization at the level of the matrix element. So we have a factorization of the kinematics. We see we lost any information about the fact that the emitter was a spin-half particle, because there's no information about gamma nu left. Okay, so that we're happy. We can factorize the kinematics, but we haven't fully factorized. We're not able to fully factorize the color information, because the color information remains trapped in the structure. Okay, so what we're going to do tomorrow is try and make sense of the soft limit and try to highlight what are the difficulties. And for the remaining of the lectures, then I'm going to work in the Cranial limit, where things are much simpler and we can actually arrive at closed form results.
Sorry.
Sure.
You wrote the icon. I cannot read. I'm sorry. The icon factor.
You're right. I wrote it in a rush. Well, actually, it's my iPad which is not responding, so that's why. It's probably telling me it's time to go for lunch.
I'm also. Oh, thank you.
The name comes from icon. So the idea is that we will achieve, well, in QED you have a factorization, and the factorization tells you that if you're emitting n soft photons, you have n repetition of this icon factor. In QCD, it's almost like that, apart from the fact you have color that gives you trouble, because you cannot factorize the color structure as well in a simple way. Any further question? Okay, so plan for tomorrow is to start from here to write down the way the matrix element factorization looks like in the collinear limit, in the soft limit, and then we'll try to apply this to do an actual calculation. Okay.